We are going to discuss about functional dependency and normalization. Functional dependency is used to specify the goodness of a relation. Functional dependencies and keys are used to define normal forms for a relation. They are constraints which are derived from the attributes. A set of attributes X functionally determines a set of attributes Y if the value of X determines a unique value for Y. X determines Y, we read it as X determines Y, holds if when two tuples have the same relation for X, they must have the same value for Y. For example, for any two tuples T1 and T2 in a relation instance R, which belongs to capital R, if T1 of X equal to T2 of X, then T1 of Y equal to T2 of Y. As said earlier, X determines Y in R specifies a constraint. Fd is a constraint on R or relation instance R. There can also be drawn as a figure. Generally, FDs are derived from real world constraints on attributes. Now we will move on to an example. The left side figure gives two relations, tables, and the right side gives the functional dependency for the B table. You can see that employee underscore project, which has attribute SSN, P number, hours, E name, P name, and P location. So SSN is a unique number which can determine E name, and P number can determine project name and project location. So it is a functional dependency, and SSN and P number together can determine hours. The FD constraint defined must hold on every relation instance R which belongs to capital R. If we have a key called K of R, then K functionally determines all the attributes in R. This is because the key doesn't have two distinct tuple values, which is T1 of K equal to T2 of K. Now we will move on to some inference rules. First one is Armstrong's inference rules. In that, first one is the reflexive rule. If Y is a subset of X, it means that X is a bigger set and Y is a small set. Then X determines Y, this FD holds. And the next one is augmentation. If X determines Y, the functional dependency X determines Y is already there, then we can augment another attribute Z into this, which is called as XZ gives YZ. The next one is transitive. You might have heard about transitive functions. If X determines Y and Y determines Z, then X determines Z. These are the set of inference rules. Some additional inference rules are also there, which is written as decomposition. X determines YZ can be decomposed into X determines Y and X determines Z. And union, X determines Y and X determines Z can be combined to form X determines YZ. Zero transitivity, X determines Y and WY determines Z exists, then we can conclude the WX determines Z also is valid. Closure is a set of functional dependencies F that can be inferred from one functional dependency, which is denoted by F plus. We can also define closure for attributes which are denoted by X plus, that are all functionally determined by X. This X plus can be calculated by repeatedly applying the above said inference rules. We can have one or more functional dependency set for a given relation. How we say they are equivalent is like this. If two sets of FDs F and G are equivalent, if and only if every FD in F can be inferred from G and every FD in G can be inferred from F. In short, F plus equal to G plus. And we will define it like this: F covers G if every FD in G can be inferred from F, and vice versa. So F and G are equivalent if F covers G and G covers F. Now minimal FDs. An FD is said to be minimum if it satisfies the following conditions. Every dependency in F has a single attribute in its right hand sides, and as the FD is minimum, we cannot further decompose the FD, or we cannot further remove any dependency from F. So that's why it is called minimal. So also we cannot replace any dependency X determines A in F with a dependency Y determines A, where Y is a proper subset of X. You can't remove such a dependency.